So at first, I'm very happy to be here at JCon again this year. And I am, of course, even more happy that you guys are all here. So otherwise, it would be pretty boring. So before we start with the talk, just a few words about me. So I think you can read the name yourself. So I have quite some experience as a software engineer over the time. I'm doing a lot of, or did a lot of Java and doing a lot of Kotlin these days. And I like giving workshops and talks like this one. So, and one a bit more personal fact about me, I also like to occasionally go wakeboarding. So if you're also a bit into wakeboarding, we can have a talk afterwards. So now, before we get a bit deeper into the topic, at first, a short question to you all. So who of you thinks they do concurrent programming at the moment? So this is quite some guys, but not a lot. So let's just go on with the question. So what actually is concurrency? Yeah. So Rob Pike once said, concurrency is dealing with a lot of things at once. And this quote gave me the implication that concurrency is maybe about the structure of the code, so how your code is built. And one thing that is necessary for code to be able to run concurrently is that it should be able to run, to be executed out of order or in partial order. So the execution of the code, the ordering of your programming code statements, that should not really matter. And what does that mean in detail? That means that even if the order of your different program parts changes, the outcome must not be affected. Yeah? So in the end, you can just move the things around in your program, so when one thing comes before the other, this should not really affect the outcome of your program. And furthermore, your code or your program parts should be able to run independently. So that they should not, these different program parts that run concurrently should not depend on each other. And if all of these things here, if your code is able to fulfill all of these things, then your concurrent code should allow for parallel execution. So with this last statement, there's also a thing to think about, that maybe concurrency and parallelism is most likely not the same. Yeah, so Rob Pike also said, if we come back to the first quote, where he said, concurrency is dealing with a lot of things at once. He also said parallelism is actually doing things at once. So these two terms are maybe a bit different, but they are often used the same, but actually they aren't. So one thing to notice here is that concurrent code must not necessarily be executed in parallel. Yeah. So now that we know what concurrency is, let us, when I first asked you, who of you does concurrent programming? So there were some hands in the air, but not that much. So why should we even think about concurrency if no one really does concurrent programming? Yeah? So I think modern software systems often use concurrency or parallelism, even if you don't really recognize it. So nowadays we use a lot of frameworks like Spring or Quarkus or whatever, and while you're programming, you're not really feeling, or it does not really feel like you really write concurrent code. But if you think like a bit deeper about it, then think about horizontally scaled microservices, for example. If you like have a program that is horizontally scaled, so the same program runs on 2 different servers or in 2 different processes, then I guess we would all expect that these 2 services handle requests concurrently. And the same is with web servers. Who of you does web applications? So do you think the web server does execute the requests concurrently? Yeah, so in most of the cases it does so, and it should. You would obviously expect it to do it, because otherwise it would be really slow on the internet if everyone has to wait for the others to finish their request, to the web server. So this is also a thing where we have some sort of concurrency or even parallelism. And the next thing, and I think this is also a thing where many can relate, because message processing or event processing, data processing is a very modern thing to do these days. And also, when you do message processing, typically you do not only have one consumer that that processes one message at a time. Typically, you would have multiple consumers. But the frameworks hide this fact often away from us. So when you like do your programming work, it doesn't really feel concurrent. But obviously, we are dealing with a lot of systems where concurrency occurs. And so maybe it's a good thing to think a bit more about concurrency. So how is concurrency done in Java? So from my point of view, or from my opinion, there are 2 different levels of concurrency in Java. And the first one is, we could have multiple JVMs. So you have different program parts that run in their own JVM, and they could run concurrently. One example would be for this horizontally scaled microservice, but also microservice architecture is a good example, I think, of this, because you have many different program parts that run concurrently. And this is one level. And the other level is using Java threads. So if you have a single JVM, to achieve concurrency here, you would typically use Java threads. And this is the topic we're going to focus a bit on from now on. So we are having a look at Java threads. But before we go a bit deeper, first the question, when is concurrency hard? Can anyone imagine when it is hard? I gave a little hint in the title of the presentation. Yeah, it gets hard when it comes to shared resources. And of course, this is not the only thing that is hard about concurrency. What also is hard is, like, for example, destructuring a program or a problem into concurrent tasks. And this is also really hard. And for this, I recommend this presentation here. This is also from Rob Pike. And in this presentation, he shows a bit how to destructure or decompose a single problem into concurrent parts. It's in the a bit in the Go environment, but I think the concepts he describes here, they hold true for most of the other programming languages as well. So this is definitely worth a read. But since we are talking now about shared resources and about Java, then we should probably talk about something like this. So we have some threads, we have some variables, and we need to So as you can see, the threads are executed concurrently. And this picture I have from the JVM specification of Java 6, of this document threads .doc. I didn't found this the same explanation on the latest spec for the JVM, but there's a really detailed chapter in the Java language specification for this. And when you think about shared resources in Java, it really gets a bit complicated. So because there are many things to consider what rules the JVM can apply. So the JVM is allowed, or so the compiler is allowed to reorder statements within a thread execution scope. There are rules about specific actions on the thread, like the happens before relationship between actions and so on. And it is really described in detail in this Java language specification. But I thought having all these really like a bit mathematical explanation on how the orders or how statements can be ordered in this case here would be maybe a little bit dry for such a presentation. So I thought, hey man, let's make it a bit more visual. So we have here these two happy guys. And obviously we see they are painters, and their task is to paint this wall they're looking at. And each of the guys should paint one half of the wall that is not yet painted. Now let's get a bit more technical here. Let's think of these two painter guys as threads, and the wall is now our shared resource. So when we think about what could go wrong, we need to think about how Java would do this with threads. So as we saw in the first picture here, you can see it here. Obviously, each thread reads the shared resource or the shared variable from the main memory. So we'll do it here as well. So, and it could be, and this is obvious, this is really not the only ordering that could happen here, but this is one thing that could happen, that both of these painters load this shared resource, the wall, and they both see the empty wall. And if they both want to paint one half of a wall that is not yet painted, they could obviously do this. And if they then write this shared resource or the state of this shared resource back to the main memory, then we end up here. So even though we have two threads, we have only one side of the wall painted. This is not what we want. But it could also end up here. So it could be the other side or here. So this is a bit you cannot really know. So this is a timing issue, and it depends on how the JVM will structure your order your statements. But I think in this case, this is not of a big problem, really, is it? Because at the end, the wall is red, and we are done here, are we? So we don't really care. But let's make this a bit more interesting. Let's look at these two guys. Now we have red and blue color. And again, our guys load the wall resource, and as the JVM so will, both see the empty wall in this state, and they start painting. Again, they paint the same part of the wall. So what may be the result here? Anyone has an idea? Is the right part of the wall now red or blue? Who thinks it's red? Who thinks it's blue? So it will have no color then. No, of course, I guess you are on the right track here. So the result could either be red or blue. So we don't really know. And what is the problem with this scenario? Or why could this scenario be problematic? Anyone an idea? Yeah, it's overridden. Yeah, exactly. And in the end, the behavior is not deterministic. Yeah, so we don't know. It could be red, it could be blue. It could be both sides of the wall could be painted, one red, one blue. We don't really know in the end. And this is, of course, problematic because typically when we write software, we want to have a specific behavior. We want it to be deterministic. Yeah? And what we saw here, this is a so-called race condition. Yeah, so one thread is faster than the other, but in our special scenario, the slower thread wins. Yeah, because the slower thread will override the result from the faster thread. So, like, yeah. So we have a race condition here. What can we do about it? When we have a race condition, we somehow need now, and if you think about painters in real life, maybe they will talk to each other. And maybe they will say, "May you paint this wall, I paint this wall, and this part of the wall," and then we're done. And we can do this in a similar way in Java. And what we can do here is synchronize the access to the shared resource. And what does synchronize mean? We need to let the two threads somehow interact with another. So they can say, okay, you go first, then I go. Yeah? And in Java, we can use mutexes, so mutual exclusive access for this. And that means that only one thread at a time, so only one painter at a time, can paint the wall. And this would obviously solve our problem because if the first painter starts painting a part of the wall, then the second painter would know that which part of the wall is already painted and then would paint the other part of the wall and we're done. And in Java, we do this either with a synchronized keyword or with locks. And both of these are things that will limit the access to the shared resource to only one thread. And you might wonder what reentrant in this case means. Yeah, so Java has an reentrant lock and reentrant read-write lock. And reentrant in this case means that the same thread can get a lock to an object multiple times. So it's reentrant. Yeah? So all other threads are blocked out. But if I maybe have a synchronized or a lock in a recursive method, and the same thread would call it over and over, it can get the lock anytime. So it is reentrant. And it is not really obvious because it's just the synchronized keyword, but synchronized is reentrant too. So you don't need to worry about the same thread accessing the same synchronized block or synchronized method. They can do it without out-blocking themselves. Yeah, exactly. And there's also another thing you can do, and this is you can use volatile variables. And what does this mean, using volatile variables? It means that the access to these variables is atomic. So when you have a write operation to a volatile variable, the JVM will make sure that other threads that need to access this see the result of this write operation. So the JVM handles the correct order of the statements then there. One thing I forgot, I'm sorry, but maybe if you have already some questions, you can now take a photo of this. We will go on in a second and type all your questions there, and I will try to answer them afterwards. I'll give you a short minute. Yes. Everyone done? Cool. So that's about how we can do it in Java. And I will have another word about how synchronize works in Java, because synchronize is like a bit, so what does it even mean, synchronize? In Java, when we use synchronize, Java uses monitors. And you might think, a monitor? How would Java use a monitor? So in this case, a monitor just means that every object in Java has an intrinsic lock, like these normal locks in Java. But it's intrinsic, so every object has one, but you don't really see it. And whenever you write a synchronized block or a synchronized statement, then this intrinsic lock is locked, and no other thread can obtain this intrinsic lock. And every object, as I already said, has a monitor, so this intrinsic lock, and even class objects have it. And again, only one thread at a time can have a lock on that monitor. So there was a lot of theory right now, but let us look at an example. So I prepared, I hope everyone can see the code, and it's not too small. No, it seems big enough. So I prepared a little example. I'm sorry that it's not about the painters, but in this case it's about the library. So we have a library. The library has books, and you can get a book and rent a book. You can of course also return a book, but for the demo we won't use it. We can await for the library to open, and we can also open the library. Then we have a customer. A customer can have a task, and a customer implements the runnable interface, and the runnable is the thing that Java threads are going to execute. And whenever you run the customer's task, then we store the result of the task in a variable. Then we have an executor. This is a very simple thing that just creates threads from the customer task and then starts each thread. We could also have used executors here for this, but I just made it this simple here. And the task is not very special. It has just an execute method. And we have, of course, the book, and the book knows if it's available. So it has an available variable. And if we now, okay, I will make this a bit bigger. So if we now look at this test, we have like a couple of customers, 2 in this case, and these 2 customers want to rent a book. And if we look at the rent book method, then we would see that before you can rent a book, you need to wait for the library to open. And then you can get a book. If the book is there, not there, return false. Otherwise, you can ask the library for renting that book, and so on. And what we would expect if the program would run correctly, that in this case, where we have only one book, here this library is instantiated with the set of books, and there's only one Lord of the Rings, Fellowship of the Ring. So if both of these customers would want to rent the same book, one of these customers should not get the book. This is what we would expect. And if we now run this test, then we will see, hey man, in most of the cases, this is true. But here in case 40, both of our customers got the book, even though there's only one there. So, and this is the exact same problem like we had before with the wall. So how can we deal with it? As I said, we have this synchronize and locking mechanism, And I, of course, prepared a bit for this. So if we now look at the test, we have now 2 tests, and one test is here with this well-known rent book task. And as you can see, we have this library await opening, and then we have here this synchronized block. And when we synchronize here over the book to rent, then the intrinsic lock of the book object will be used here. And this means this code here between these 2 curly braces can only accessed by the thread that holds the lock onto this same book object. So every other thread needs to wait. And if we do it like this, then we can run this test here like 1,000 times, and it will always succeed. Yeah, so no special thing here to do. It's just that easy in this case. But the synchronized block is only one possibility to use the synchronized keyword, like here. We can also have the complete method synchronized. And if you do this, then the monitor that is going to be used is the monitor of the object this method belongs to. So it will log, in this case, it should be the test shared resource. Yeah, and if we now run the second test with the synchronized method, we will realize something strange. And what we realize here now is that, okay, somebody can rent the book, but the other guy, we have again 2 guys here that would want to rent a book. The other guy does nothing but waiting. How does this come? As well as in the rent book method, we also wait for the library to open in the sync rent book method. And when we look here, what happens when we wait for opening? We have again here the synchronized block, and we just wait. And as this method is also synchronized, now it gets a bit tricky. Only one of these customer threads here can enter this method. And when we call library open, library open does notify all, but not all of our expected threads are really waiting for the object monitor. It's only one because the method is synchronized. And that means when we run here in this notified block, in this library open block, the first thread that got the lock on this sync rent book method will just execute, and then the second thread will try to enter this method and also waits for the library to open. Yeah, so now it's stuck. We're in a deadlock because nobody opens the library a second time. So now there are a lot of things you can do to get to deal with this problem. One thing is we could, of course, work with the state here in this library. We could have a variable that the library is already open and not go into waiting state when the library is already open. But we also can just extract here the important part to another method. Now we can make this method synchronized and put that one away. And if we now run this test again, then now everything should work. So as you have seen, you have to be a bit cautious about the synchronized method and what happens within this synchronized method, because when you're using waits and notifies, then you could easily produce deadlocks if there's no one to notify a waiting thread. So that's about using synchronized. Another interesting thing to do in Java, I will roll back all these changes, is using locks. Yeah. And locks work a little bit like this synchronized thing. So you can just instantiate here this reentrant lock or reentrant read-write lock. And in our rentbook method, we can now obtain a lock by simply calling lock on our lock object. And now this the part after this lock is blocked for every other thread. There's only one thread that can lock this lock, and all the other thread needs to wait. But one important part is that you really need to unlock this lock again. Otherwise, you're again stuck in a deadlock. So nobody unlocks this lock, and then you will never be able to execute this block from another thread. And it is really recommendable to unlock your lock in such a finally block. Because when I put it here, just right under, just right here, yeah, this should suffice. But what if our rent method now throws an exception? Then this booklock unlock method will never be called, and we are again stuck in a deadlock. So if you're using locks, unlock them in a finally block, so that you can be 100% sure that the lock gets unlocked again. And we can now run this method again, and the outcome should not be very surprising. So now we have, again, all tests green. Another demonstration here about the read-write lock, and this is also a bit interesting because read-write locks work in a way that when you obtain a read lock, like here in this, where's the other method here? Like here in this check book is available method, then this means every thread can obtain a read lock. So there's no blocking operation here unless some thread obtains the write lock of this lock. So we can see it here. If we now have this second test, we have now 2 customers just checking if a book is available. And if we run this, they should all be happy because the book is always available. But if we then add a customer here that rents a book using the write lock, then all of a sudden this test fails because the first one, the renter, saw the sets this flag available of the book to false, and so for this checkbook is available, these ones only see that the book is not available and will return false. And this is because they wait until the write lock is unlocked again. So this is very useful if you have a shared resources that has maybe a lot of write access that is very unproblematic, but occasionally has a lot of read access that is unproblematic, and that could be easily executed concurrently without any conflict, but occasionally has write access, writes to this shared resource, and you want to make sure that if a write occurs, the reads will see the new state immediately. So that's it about the demo. Let's head back to the presentation. So this was all about like regular threads in Java, but whoopala, we know there is one new thing in Java 21, and this is the virtual threads. And virtual threads are super cool, but even virtual threads, they under the hood use platform threads, so-called carrier threads, and they are especially useful if you have concurrent code that has that is blocking, because when code on a virtual thread is blocks, then the carrier thread can be used by another virtual thread, and this is the whole magic. But there are occasions when the virtual thread pins the carrier thread, which means that it exclusively locks it for its own. And this is exactly the case when you use the synchronized keyword. So if you use synchronized, then the thread, the virtual thread will pin this carrier thread, and it won't be available for other threads, for other virtual threads. So you should try to avoid this and use locks instead, because in that case it won't be like this. So in this article that I added here, it is said if the synchronized time is very short, it should be, and you use it rarely, then it should be no problem. But I guess the best thing here is just to avoid the synchronized keyword and use locks instead. And okay, so far, if you have access to a shared resource in a single JVM, but what we have nowadays often is distributed systems. And when we have distributed systems, things are getting a bit more difficult, because we have no JVM that can handle this access through like a synchronized keyword or locks. So often when we have distributed systems, we will synchronize over the database or file system, maybe using log files or something like this. And there is a consideration here to make, and this is using optimistic versus pessimistic locking. And pessimistic locking is what we saw with the Java synchronized block and the locks there. Because it will give you exclusive access to your resource. Whereas optimistic locking works a bit different. So with optimistic locking, everyone has access in the first place, but when you try to write back your data, then you first check if the state of your shared resource changed in the meantime. And you're only able to write your changes back if no one else changed your resource in the meantime. So this is often used if you have access to shared or write access to shared databases, but there are also other things to consider here, because if there happens an exception there, then you need to handle it somehow, like the optimistic locking exception. What I can recommend in this case, for example, for automated systems where you cannot really decide what to do in this case, you can use distributed locking, and Spring Integration offers a nice little library for this. And this gives you then in your programming code, first of all, it uses a shared database as well, so you need a shared database, but in your programming code, you can just use Java locking semantics, and that makes it a bit more controllable. So you don't have to deal with extra exceptions or something like this, like optimistic locking exceptions. You can just use normal Java lock and unlock mechanism to synchronize your code here. Yeah, so I think this is at least worth a thought if you're having problems here in this case. So, yeah, and you do not need to deal with optimistic locking exceptions. So this is it from me right now, and I think we still have some time for questions. And can we get the slide and the source codes? Of course you can. I have not made them publicly available yet, but I will make them available. Maybe it would be easier to use structured concurrency, but I would probably wait until the features really out of the state of out of the preview state for this. Even so, for productive code, I used a bit structured concurrency in Kotlin, and I think it's a nice thing to use. But in Java, probably for critical code, I would wait until the features done completely. How can I avoid deadlock? Yeah, you can you can avoid deadlocks if you use logs in Java code. So it depends a bit on where your shared resource is. But when you use logs and use this try finally pattern, then you're almost safe from deadlocks, because you know when this try block is done, then your log is definitely 100% released, and you should be extra vorsichtig, extra careful when you should be extra careful when using wait and notify, because you should really make sure that one thread is not waiting forever. Yes, it is feasible, or I have done it using DB level log for multiple JVMs, and it worked out quite well. As I said, I did it with Spring integration, and it does exactly that. It gives you locking semantics within the Java code. And now the question is gone. Okay. No worries. I cannot really. Maybe you could also use something like Redis or to use it, but it's basically the same, but just another type of database. Can I use synchronized Java collections instead of a synchronized block in your library example? You could use it, but I guess it would not help in this case, because I can show it. I will show it shortly, because what is the real problem? The real problem in the library example, and that's a bit confusing now here for the example, is that we're checking here this is available variable from the book. And the is available variable from the book has nothing to do with this map. Yeah, so this is a different scope just. So if you if we would have manipulations here in this map, like puts and gets, then we could use like concurrent hash map. But in this case, the variable that makes the problem is somewhere else, and it's in the book. And it's this one. What could help here is maybe use a volatile variable. So you could use this. There is no timeout, I think, in the synchronized methods, but you can have timeouts in the wait, if I'm not mistaken. So you don't need just to wait forever, and if you have like critical path in your application, you should definitely use a timeout in the waits to not accidentally get into a deadlock. Or even reading while writing. This is a good question. Typically, the database itself has some techniques here, and one technique that you could use is like optimistic locking, as I explained. So typically in databases, this is done with like a version column that is increased every time a write occurs. So you could use this, and this is pretty common, I think. And another thing would be using pessimistic locking. But there you need to be really careful when using this, because there you could easily produce deadlocks. Typically, databases are thread safe, but when there is like multiple writes to a resource, then it is a timing issue on what write would win on the database. So you need to synchronize it somewhere. So the database won't like crash or do something wrong, but it's like your responsibility to make sure the data is consistent in the end. So in this case, it's more about consistency. The database itself should be thread safe. That we have always used them in the same order. Okay, I need to think about this. Maybe we can talk about this in person. Yeah, immutable objects is a good thing to do to avoid like manipulating shared resources. But at some point, typically, you would love to have your state somewhere. So not all objects can ever be immutable. Otherwise, your application would be pretty static, and maybe that's not a lot of fun. So at some point, you will want to write a state somewhere. Maybe a shared resource like a database. Maybe you have a shared resource in memory where you put your state. So immutable objects is generally a good thing, I think, to avoid a lot of problems. But in the end, you want to have store your state somewhere. So immutable objects won't help forever. Cool. I guess that's it. I hope you had some fun. I had some. So see you around here. Bye.